Hello and welcome to the Theory of Computation lectures. In this class, we'll talk about Epsilon NFA. So we have already discussed about DFA and NFA. In DFA, given a state and an input symbol, we can determine what is the next state. For example, if you look at this DFA and I ask you if the current state is A and the input symbol is 0, what is the next state? You can surely tell me that the next state is B. But for an NFA, it is not possible to determine the next state even if the current state and the input symbol is given. For example, in case of this NFA, if I ask you if the current state is A and the input symbol is 0, what will be the next state? You cannot say for sure because it can be either B or C. Now, what is an Epsilon NFA? In case of an Epsilon NFA, again, it is like an NFA where you cannot determine the next state given the current state and the input symbol, but there is also another difference, and that is from one state to another state, a transition does not need an input symbol. So we can denote a transition from state A to state B without any input symbol, and we denote it by epsilon. Epsilon transition means there was no input symbol, yet the machine transitioned from state A to state B, or in this case even state A to state C. So that is the basic difference between NFA and an Epsilon NFA. Okay. In case of an NFA, to make a transition from one state to another, an input symbol is required. Whereas in case of an Epsilon NFA, even without any input symbol, the system can transition from one state to another, and we denote such transitions as epsilon transitions. So why do we go for Epsilon NFAs? Because the design of Epsilon NFAs is much simpler than DFAs and NFAs. Let me give you an example. So let us design a DFA over input alphabet 0 and 1 to accept strings of the form 0 to the power m, 1 to the power n, where both m and n are greater than or equal to 0. Okay, so what kind of language would this machine accept? So of course, since it is saying that 0 to the power m, 1 to the power n, and m or n are greater than or equal to 0, so when m and n are both 0, the system should accept the empty string or the null string, right? Now, when m is 1, n is 0, it should accept only 0. When m is 0, n is 1, it should accept only 1. And there onwards, it can accept 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, and so on. Note that the order of the symbols are important. It can accept any number of zeros followed by any number of ones, right? But once it has received a 1, it cannot receive any more zeros. So the order of the symbols, input symbols, is important. Basically, the machine should accept a number of zeros followed by a number of ones. Okay, let us design a DFA to accept this language. So we start from a state A, which is the initial state, and then on A, if we receive 0, we will stay in state A because it's also a final state. Why is this a final state? Because the empty string or the null string should be accepted. So whenever a null string should be accepted by a DFA, the initial state becomes the final state. So in the initial state, as long as we receive 0, we will remain there. Then moment we receive a 1, we go to another final state, say state B. And in this state, we will remain as long as we get 1. Right. So now what happens if we receive a 0 in state B? If we receive a 0 in state B, then of course that string cannot be accepted, because if we receive a state B, that means we have received some zeros, then some ones, then another 0. That is not possible according to our rule. So we will go to a dead state C, and of course since C is a dead state, as long as we get ones and zeros, we will remain in state C. That means there is no way out of this state. Okay, so that basically defines the DFA to accept strings of the form 0 to the power m, 1 to the power n. Now let's design an Epsilon NFA for the same problem, where we are going to accept strings of the form 0 to the power m, 1 to the power n. That means a number of zeros followed by a number of ones. So in case of an Epsilon NFA, remember, we don't need an input symbol to make a transition from one state to another. So we can start our design from an initial state A, and as long as we receive 0, we can remain in state A, and then we make an epsilon transition, that means a transition without an input symbol, to state B. Now in state B, if we receive 1, we are going to remain there, okay, and that basically completes the design of the Epsilon NFA. Now a few things you should note over here is that, firstly, why is A not an initial state in this machine? Because we have to accept the null string, right? So will this machine accept the null string? The answer is yes. Why is so? Because, for example, when the machine starts off, we are in the initial state A, and we can make a epsilon transition to state B, which is the final state. So even the empty string will be accepted, right? Now, will the machine accept a number of zeros? Yes. If you get 0 in state A, as long as we are in state A, we are going to remain in state A, and then we can make a finally epsilon transition to state B, which is the final state, and it will still accept those strings. Will it accept only 1? Yes, because we are in the initial state, and then we can make an epsilon transition to state B, then we can receive a 1 and remain there. So it will accept that. So basically it will accept all the strings of the form 0 to the power m, 1 to the power m. So basically that tells you that the design of Epsilon NFA is much simpler than the design of the DFA that we just saw. So we designed NFAs because they were simpler than DFAs, and now we are going to see the design of Epsilon NFAs, which are even simpler than NFAs. Now, what is the difference between DFA and NFA? We saw that basic difference between DFA and NFA is in the transition function, where the transition function of a DFA is a mapping from the Cartesian product of Q and sigma to Q. That means if you are given a state and an input symbol, you can tell what is the next state. In case of an NFA, the mapping is between the Cartesian product of Q and sigma to the power set of Q. That means in case of an NFA, if you are given a current state and an input symbol, it can be any combination of the states of the NFA. Okay. In case of an epsilon NFA also, it is basically consisting of the same 5 tuples, but the transition function is again different. In case of epsilon NFA, the transition function is from a Cartesian product of Q and union of epsilon and sigma to the power set of Q. Now that means that if a current state is given and either an input symbol or epsilon is given, you can still map it to any permutation of the states of the Epsilon NFA. Okay. So basic idea of designing a finite automata is our goal is to design minimal DFA, but directly designing minimal DFA is sometimes difficult. So we start with a DFA and then design a minimal DFA. But in certain cases we have seen that design of DFA is also quite difficult. So we start with NFA, which is simpler than designing DFAs, and then go to the design of DFA. We can convert the design of NFA to design of DFA. But now we will see that even simpler is to design epsilon NFAs, and then we can design epsilon NFAs and then convert it to NFAs. So in our next few classes, we will focus on how to design epsilon NFAs and how to convert them to NFAs. Thank you.